Hello everyone, my name is Konda. I'm a third year PhD student from the Department of Mechanical Engineering at the University of Nevada, Reno. The title of my paper is A Twisted String Actuator-Driven Soft Robotic Manipulator. This work has been co-authored by my colleagues David Bombara, Ryan Coulter, and also by my advisor Dr. Zhang. The overview of my presentation is as follows. First, I will talk about the background of our work, where I will introduce the concepts of soft robots and artificial muscles. Then I will discuss our motivation for doing this project. Next, I will introduce twisted string actuators and their properties. After that, I will get into the details of the design of the proposed robotic manipulator, the materials and methods used to realize it, and the experimental results, which include experimental characterization, modeling, and control of the behavior of the manipulator. Finally, I will conclude my presentation with comments on future work. Soft robots are one potential solution to make robots more ubiquitous in domestic scenarios and areas which demand close interaction with humans. Soft robots have many desirable properties including low mass, compactness, low cost, and the ability to facilitate safe environment for humans around them. Some examples of soft robots are presented in this slide. On the top, we present a dielectric elastomer actuator based crawling robot by Dudata et al. On the bottom left, we present a pneumatic actuators based crawling robot by Shefford et al. And on the bottom right, we present a shape memory alloy actuators based biomimetic soft gripper by Kim et al. Soft robots are realized using soft materials and utilize soft actuators and artificial muscles as driving mechanisms. Artificial muscles are materials which change shape upon the application of external stimulus such as heat or pressure. Unlike traditional actuators, artificial muscles exhibit many advantageous properties such as compliance, low mass, and high power to weight ratio. Commonly used artificial muscles are pneumatic actuators, shape memory alloy actuators, and dielectric elastomer actuators. Although soft robots are highly desirable, realizing high performance soft robots is challenging. This is mainly because the soft actuators and artificial muscles used to drive them have one or more limitations. For example, while pneumatic actuators exhibit good force and strain outputs, their inclusion means including pumps which could affect the compactness of a system. Similarly, shape memory alloy actuators produce low forces and have low bandwidth and highly nonlinear behavior. Furthermore, since SMAs utilize thermal actuation, they could potentially damage the body of the soft robot in which they are employed. Likewise, dielectric elastomer actuators require complex manufacturing procedures which could be difficult to realize. DEAs also require high voltage inputs in the ranges of up to 20 kilovolts and even then generate insufficient force outputs. Therefore, there is a need to investigate the use of other alternatives in order to realize high performance soft robots. Which is why in this study we investigate the use of twisted string actuators to drive a soft robotic manipulator. Twisted string actuators are artificial muscles which efficiently convert rotational motion into translational motion. They consist of two or more strings attached to a motor, and by inducing twists in the strings, contraction is obtained. This is shown in the top video. TSAs are capable of generating up to 30% contraction of their initial length, have a power density of 0.5 watts per grams, and exhibit 75 to 80% efficiency. They also have a very high life cycle. TSAs exhibit many advantageous properties over other commonly used artificial muscles such as high force generation, low nonlinearity in behavior, compact footprint, and are also easy to fabricate and assemble. In comparison to a spooled motor actuator, previous studies have shown that TSAs exhibit higher force outputs for similar torque inputs while also exhibiting more muscle-like motion. Due to these desirable properties, TSAs have been applied in advanced robotic and mechatronic applications such as robotic fingers, robotic arms, and exoskeletal technology. Couple of examples are presented in this slide. On the bottom left, we present the DexSmart robotic arm by Palli et al., which utilizes around 20 TSAs to generate a wide range of motion. On the right, we present an exoglove by Sabedze et al. Used in rehabilitation, which utilizes 4 TSAs. Despite having many desirable properties, TSAs have never been applied before to drive soft robots, mainly because of the inclusion of motors and inextensible strings. Despite inextensibility, the flexibility of the strings could be sufficient to facilitate inclusion in soft robots. Furthermore, by using stretchable strings, the compliance of TSAs could be further enhanced. However, including motors into the design of a soft robot could be potentially challenging. Meanwhile, the application of TSAs to drive exosuits and exoskeletal gloves shows their strong potential in applications related to biomimicry and bioinspiration, and also in fields requiring close interaction with human beings. Furthermore, as it can be inferred from the figures, due to the muscle-like behavior, TSAs could present many advantages when used to power soft robots. For example, due to their high force outputs, TSAs could drive relatively larger soft robots which exhibit high performance, which is why in this work we present a soft robotic manipulator driven by TSAs. The design of the proposed robotic manipulator was inspired by previous studies based on soft robotic fingers. However, the inclusion of TSAs meant that instead of being restricted to a finger, the robot could be scaled up to be a manipulator. The design of the soft arm was biomimetic and inspired by an elephant trunk. To facilitate multi-degrees of freedom provided by a continuum robot, the design of the soft arm used 3 TSAs in conjunction to bend, retract and orient the end effector in multiple directions. The introduction of 3 degrees of freedom meant full control of the movement of the robot in its workspace without any under-actuation. The elephant trunk based design of a soft robot could allow for avoidance of obstacles of unusual shapes in complex environments. Additionally, the natural compliance of the soft robot would allow for safe human-robot interaction. The design consisted of a soft cylindrical body held vertically by a base. The body had 3 channels to accommodate strings of the TSAs. The base was used to house the motors of the TSAs. Furthermore, the base was designed such that it consisted of 3 parts. This was done to ensure quick and efficient 3D printing of the base. The top cap attached at the top of the soft body restricted the strings from untwisting. The soft body of the robotic manipulator was made with smooth-on 0050 silicone. This silicone was selected due to its predominant use in related literature and also because it was not toxic and safe to handle. The mold for the soft body was designed such that it was easy to 3D print and was disposable once the body was cast. Each twisted string actuator consisted of a pair of ultra-high molecular weight polyethylene strings and a brushed DC motor from Pololu. UHMWPE strings were used due to their predominant usage in related literature, and the 2-string configuration was used because of its efficiency in generating desired forces while being relatively compact. The diameter of the strings was 1 mm. An inertial measurement unit from SparkFun, which was attached at the top of the soft body, was used to measure the bending of the manipulator. The mass of the manipulator was 710 grams, length was 308 millimeters, and diameter was 40 millimeters. The total cost to realize the proposed robotic manipulator, including all materials, was around $240. Without loss of generality, we describe the actuation mechanism when only one TSA is actuated. The actuation mechanism of the proposed robotic manipulator was as follows. Upon the activation of a TSA, the corresponding side of the manipulator reduces in length due to the contraction of the TSA. Since the soft body is flexible, reduction in one side results in the extension of the length of the opposite side. Due to this phenomena, the manipulator bends in the direction in which the activated TSA is present. By activating multiple TSAs simultaneously, the manipulator can be bent in different directions. Coming to the experimental results, firstly, the motor rotations bending angle correlation is discussed. For this experiment, only one TSA was actuated. The input sequence applied to the TSA is shown in the figure on the left, and the corresponding bending angle output is presented in the figure on the right. The input consisted of 2 cycles of monotonically increasing followed by monotonically decreasing motor rotations with a step size of 1 rotation. For this step size, the proposed manipulator settled at a steady state value in around 2 seconds. 2 cycles were applied to check the repeatability of the manipulator. For 22 motor rotations, a bending angle angle of around 57.2 degrees was obtained, while the manipulator was capable of achieving bending angle of around 97.4 degrees. Repeatedly applying such inputs could damage the soft robot. In comparison to other similar structures, the bending angle achieved by the proposed robotic manipulator was superior. Furthermore, the steady-state motor rotations bending angle correlation was captured using a second-order polynomial. The average modeling error was 1.08 degrees. Considering the range of the bending angle to be from 0 degrees to 57.2 degrees, this modeling error was deemed to be satisfactory. Meanwhile, as it can be seen, the correlation was observed to be non-linear in nature with a hint of mild hysteresis in the behavior. Hysteresis is a phenomena where the current output of the system not only depends on the current input but also the history of inputs applied to the system even under quasi-static conditions. However, in comparison to soft robots powered by other artificial muscles, the observed hysteresis was less significant. While the nonlinearity in behavior could be mainly attributed to the nonlinear behavior of the TSA itself, hysteresis in the correlation could be due to the material properties of the silicone. Secondly, the motor rotation stiff force correlation is presented. The input sequence applied to the TSA is shown in the figure on the left, and the corresponding tip force output of the manipulator is presented in the figure on the right. The tip force was measured by attaching a load cell to the tip of the manipulator such that the connection between the load cell and the manipulator was perpendicular to the central axis of the manipulator. The input sequence consisted of one cycle of monotonically increasing followed by monotonically decreasing motor rotations with a step size of 1 rotation. For this step size, the manipulator settled at a steady state value in around 2 seconds. At 15 rotations, the manipulator exerted a force of 508 millinewtons. The motor rotations were restricted to 15 rotations because at more than 15 rotations, the manipulator started to achieve an S-shaped posture due to the constraint at the tip in form of the load cell. Furthermore, the steady-state motor rotation stiff force correlation was captured using a third-order polynomial. The average modeling error was 18.46 millinewtons. Considering the range of the force to be from 0 to 508 millinewtons, this average modeling error was considered to be satisfactory. As it can be seen, similar to the previous case, the correlation was observed to be nonlinear in nature with a hint of mild hysteresis in the behavior. To control the behavior of the proposed manipulator, firstly, open loop control was realized. The control was realized by inverting the models obtained before such that for a given desired bending angle, the required motor rotations were obtained. The desired bending angle was a sequence of random numbers. This type of sequence was selected since it covers nearly the entire range of the manipulator's outputs. The results are presented in the figures. As it can be seen, decent results were obtained with the average control error being 0.74 degrees. Considering the average modeling error to be 1.08 degrees, the obtained control performance was deemed to be satisfactory. Another minor source of error could be the control error of the motor in achieving the desired motor rotations. The motor was controlled using a proportional controller and had an average control error of 0.08 revolutions. The gain of the proportional controller was tuned experimentally such that very little oscillations were obtained. While the motor was controlled in a closed loop manner, this mode of control was deemed to be open loop from the bending angle perspective since the control input did not utilize bending angle measurements. To further enhance the control of the proposed manipulator, closed loop control was realized. The control was realized by utilizing the IMU measurements to compute the error between the desired and actual bending angle. A proportional controller was used to maintain simplicity and the gain was tuned experimentally such that very little oscillations were obtained. The results are presented in the figures. As it can be seen, decent results were obtained with the average control error being 0.38 degrees. Furthermore, the inclusion of closed loop control reduced the control error by nearly half in comparison to the open loop control. The rise time of the manipulator was found to be 8.03 seconds. The friction between the strings and the silicone could play a role in the response time of the manipulator. However, studying the dynamic response of the proposed manipulator was beyond the scope of this study and will be addressed as a part of future work. In conclusion, this work provides the first study to examine the application of TSAs to drive soft robots. The proposed robotic manipulator, while being low cost, exhibited superior performance in comparison to other similar structures, which could be mainly attributed to the inclusion of TSAs as driving mechanisms. The behavior of the proposed robotic manipulator was experimentally characterized, modeled, and controlled. As a part of future work, we plan on developing physics-based models to capture the static and dynamic behaviors of the manipulator. The models will be developed using existing TSA models which have been studied extensively. Furthermore, we plan on extending this study by attaching a soft gripper to the tip of the manipulator and investigate its grasping and manipulation capabilities. Lastly, the study could be extended to cover other types of common soft robot structures such as soft mobile robots, continuum robots, and soft robotic grippers. Thank you for your attention and have a good day.